The North Texas Research Park, located at 3940 North Elm Street off Bonnie Brae, was bought by the University of North Texas from TI back in 2004. Since then, UNT has renovated this building to house its research for the College of Science and Engineering. The building is up and functional, offering a range of labs and classes to the students currently attending. However, only about 1/3 of the building is up and running, while the remaining 2/3 is still receiving a makeover to accommodate the studies and research the department intends to offer. At the moment, the building houses about 45 full-time faculty members, which are currently accommodating about 1,400 students. Once completed, this complex, which sits on 290 acres of land, will offer students an almost endless potential of knowledge and research that will give each student the equipment and materials needed to make any idea or hypothesis within reach. One of these departments is the Department of Material Science and Engineering. Let's head on in and see what kind of technologies and research that this department is currently working with.
Hi, I'm Dr. Brian Gorman of the Material Science and Engineering Department. Today I'm going to give you a tour of our electron and ion microscopy lab. Follow me. All right, we're in the Department of Material Science and Engineering within the College of Engineering out here at the UNT Research Park. Material science and engineers are interested in things about how to manipulate materials and improve their electrical, mechanical, and optical properties. Usually we do that by doping materials with different elements, adding carbon and oxygen to different materials. But how do we find out where we put the elements and how they affected the electrical properties? Well, that's where these new instruments come in. We've been lucky enough to bring in some really state-of-the-art equipment in the past couple of years. 3 instruments in particular make us unique within all of North America, including the national laboratories. This particular instrument that I'm standing in front of is the high-resolution transmission electron microscope. This instrument has 200,000 volt electrons that come down, shoot through a sample, and we measure what comes out the bottom. The advantage of using electrons as opposed to light is resolution. With this particular instrument, we can get atomic resolution. We can see individual atoms and identify their composition. On this particular image on the screen, we can see individual white spots corresponding to individual silicon atoms. These silicon atoms typically make up the brain of your microchips in your computers. What we look at are dopant atoms inside of this material that help it run faster and help you get more computing power out of your instrument. We're next door now in the materials science department, next to our other instrument that makes us quite unique. This is a dual beam field emission scanning electron microscope and focused ion beam. Instead of putting electrons through our sample, we're now going to scan them across the surface and look at what the surface topography looks like. In addition, it also has an ion beam column, which just allows it to do nanoscale milling on different materials. So we can go through and cut out an individual transistor in a microelectronic device. We can move it around with our nano manipulator here. We can deposit platinum, put machines together. This is Dave Dirks. He's one of our top graduate students. He is currently making atom probe samples with the ion beam. We'll get into the atom probe in just a minute. This is a real-time movie of the UNT logo getting milled into a silicon wafer. The size of this entire pattern here is 8 microns across, which means about 10 of them would fit across the diameter of a human hair. But what this allows us to do is look at site-specific areas, such as a transistor, pull it out, and go in and determine the atomic composition of the individual devices. We're now down the hall in the Material Science and Engineering department from the previous 2 instruments you've just seen. What you're looking at is the local electrode atom probe. It's quite complementary to the previous 2 instruments in that we can take out a single transistor with that focused ion beam instrument, polish it into a needle, put a really high electric field on it, and extract atoms one at a time. When we do that, we can measure the individual atomic composition. If we then go to the electron microscope and determine their position, then we have a full reconstruction of what the atomic structure of each individual material looks like. Most of the components that you see on this instrument are to maintain the vacuum levels. This instrument, in order to measure individual atomic compositions, needs to run at a vacuum level 1/1000th that of space. So we're very, very interested in maintaining high vacuum, and that's what all this equipment is mainly for.
Believe it or not, this is just a small segment of research that occurs in this building. Again, keep in mind that only part of this building is up and running, and this much research is already taking place. Far more renovation is still underway, so tune in for future segments unveiling the research and potential this building has to offer. For NTscene, I'm Sam Hobbs.